Hey, honors pre-calc. Welcome to lesson 3.2, logarithmic functions. This is our second lesson in unit 3. We are going to today evaluate and graph a logarithmic function. The essential question is, how do logarithmic functions compare to exponential functions? And that phrase, an exponential function, is something that you should already know. That's what our first lesson was about. That's any expression where the x is in the exponent. You should also need to know about the number e going into this lesson, which was also in our previous lesson. We're going to be looking at that again. And here's something that we're going to be able to do. You're going to be able to use the one-to-one property of logarithms to simplify the expression seen here. And this is pronounced log base 4 of x squared minus 6 equals log base 4 of 10. When you're talking about these, I really want you to be able to say it like that, right? Log base 4 of 10. You shouldn't just say log 410 or log little 410 or something like that. It's log base 4 of 10. That's the vocab that we're going to use, okay? So I will pause this and we will pull out the notes. Okay, so I wanted to start off this lesson a little bit different because when I think about logarithms and I think about introducing them to students, I think that the idea of a word, well, something that is also a word in the English language, log, appearing in a math equation just seems kind of weird, and it doesn't look like other things in math. But I want to reassure you that it is a pretty standard, normal thing to see in an equation. And it's not that crazy or foreign of a concept. It's just written in a different way than we're used to seeing. Right? So how I want to start is just by asking the question, how do you solve for x when x is inside of an exponent in an equation, right? So much about math is solving for x. And we saw in the last lesson, if you have something like 3 to the 4th equals 3 to the x, well, we have the same base. So then you can just make the exponents equal to each other and we can solve for x. But what if it's something where that doesn't work out as nicely? What if we have 15 equals 2 to the x? How do we solve for this x? We can't make 15 have a base of 2. There's no 2 to some power that equals 15. 2 to a certain power equals 16, but not 15. So what, am I going to just have to type decimals into my calculator as exponents until I get close? Am I going to have to write try 2 to the 3.5, 2 to the 3.6, 2 to the 3.7? See if any of those get closer and closer to 15 just to guess x. Well, that's one way of doing it. But that's not ever going to get you an exact answer. And that's not really like guessing and checking is not something that we want to rely on, right? And so normally to solve equations, we use inverse operations. So as we know, the opposite of addition is subtraction. The opposite of multiplication is division. The opposite of squaring something is square rooting something. But what's the opposite of the x being in an exponent? We don't know. There's nothing we can do to both sides of this equation to get that x out of there, except that there is, and that's where logarithms come into play. The logarithm is the inverse operation of the x being in the exponent. Now, it doesn't really look opposite, but it is, right? So maybe if I was inventing math or discovering it, I would decide that the opposite of a number raised as an exponent should be maybe like a subscript, something down here. But that's not what it is. Instead, we write it as a log. And so I have a couple initial questions up here at the top of the page. I'd like you to write these down. You can do that over here on your notes. Would be a great place to put that. So if we start with the exponential form, right? This is kind of what we're used to. We could say that some number equals a to the y. And I'm just going to give each of those a letter so that we can see where each one of those is. So if x equals a to the y, that can be rewritten as y equals log base a of x. And so another way of thinking about a log, it's just saying a to what power equals x. right? Because look at it over here. If we had a number here and a number here, we'd say a to what power equals x, and that would be the answer, right? A to what power equals x, and the y is the what, right? So let's try to use that to solve these three initial questions here. Y equals log base 4 of 16. So if we rewrite this in our exponential form, it would be 4 to the y power equals 16. Again, log base 4 of 16 means 4 to what power equals 16. So the y is in the exponent. We don't have to do that much work here. Let's just think about this. All of these initial ones are going to turn out pretty nice. We think 4 to what power equals 16? Well, 4 times 4 is 16, so the exponent should be 2. If we try the second one, we say 2 to what power equals 8? And that should be a 3. And for the third one, we have 5 to what power equals 3,125. And I had to use my calculator for this one just to try a couple exponents, and the correct answer is 5. So we get 5 to the 5th power equals 3,125. So that's kind of how these are inverses. If we are trying to get rid of a variable that's in an exponent, we can use a log to help with that if we take the logarithm of both sides. And we'll see more about how to do that in the next lesson. But for now, we're just going to learn some properties of logarithms, what the graph looks like, so that we can kind of have a basis for this before we really apply it as an inverse in an equation. I'm going to pull out my notes. All right, so here are the notes. We've been looking at this logarithmic function setup already. We're going to use this inverse property, as I've already showed you a little bit. There's some simple log properties here that we'll come back to, other things, and then here's where e comes back. We have this natural log function. So whenever you see ln, it's just another way of saying log base e. Log base e gets its own look because e is such a common number to see whenever you're dealing with exponential functions. So log base e is going to show up a lot, and we just write it as ln, which stands for log natural, or natural log. Okay, so let's look at example 1. Use the logarithm inverse property to evaluate each expression. So what we're going to do here is imagine that we have an equals y here. Give me 1 second. Okay, sorry about that. Imagine that we have an equals y here. We are going to try to figure out what this expression equals without using a calculator by rearranging it using our exponential form, right? So this is logarithmic form. Let's switch it to the exponential form. So we say 2 to the y power equals 32. And I know that 32 is 2 to the 5th power. I could kind of think through that on my fingers if I wanted. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So we have a y of 5. And that's what we're going to do for all of these. So I'm going to write these out. This one is 3 to the y equals 27. 27 is 3 to the 3rd power. So this is going to be y equals 3. This one is 4 to what power equals 2. And 4 is 2 squared. So I could rewrite this side if I wanted, like this. So 2 to the 2y equals 2 to the 1st. So we have 2y equals 1 and y equals 1/2. It's kind of a roundabout way to do that. You could also think about that. We could rewrite this side as 4 to the 1/2 because 2 is the square root of 4, and then you'd see right away that y equals 1/2. But anyway, we got that answer. We keep going down here. We get 10 to what power equals 1/10. And for this one, you need to remember the property that if I raise a number to the negative 1st power, it's like flipping it to the denominator. So y is going to be -1. In the next one, we have 3 to what power equals 1. and you need to remember that any number to the 0 power equals 1. And for the last one, we have 2 to what power equals 2, and you need to remember that any number to the first power is itself. So y is 1. All right, so there's your brief introduction and a good review of exponent properties. We go to example 2, evaluating logarithmic expressions with a calculator. Evaluate each logarithm with a calculator rounding to the nearest thousandth. All right, so notice that each one of these is log base 10. On your calculator, if you just click the log button, so if I bring this over here, there is a button, and depending on your calculator, it might be somewhere different, but there should be a shortcut log button. If it just says log, and when I type it in, for the first one, I'm going to do 2 log of 2.5. If there is no base, the default base is 10. So even if we didn't write 10 here, it would mean the same thing. So I could write that this equals 2 times log of 2.5. And that's the same thing as log base 10. You don't have to write the base 10. If it's any other base, you have to write it. But here I'm going to round this to 3 decimal places, so it's going to be 0.796. Okay, that might be something that we want to write down. Log base 10 of x is the same thing as log of x. Okay, let's try letter B. Letter B, so we're going to type this in as just log of -2. Non-real answer. Okay, so that is correct. And let's think about what that means. Remember, we said a log means 10 to what power equals -2. Well, there is no real number, positive or negative, that I can raise 10 to get a negative number. It just doesn't work. 10 to any power is always going to be positive. Even if I raise 10 to a negative power, it just means 1 over 10, which is still positive. So we can't get a real answer in letter B. Let's try letter C. Log of 1/3. -0.477. All right, and it is possible to get a negative answer, but it's not possible for this to be negative. Remember, this is serving as the exponent. It's 10 to this power equals 1/3. All right, so that's the whole front side. Let's flip on over to the back. Use the simple properties of logarithms to simplify each expression. So let's think this through. In this first one, it's 4 to what power equals 1. And we need to remember that anything to the 0 power equals 1. And that's one of our properties from the front side. We said log base A of 1 is always 0. So the A can be any number. And it even says y, which is what I was just saying. In letter B, log base √7 of √7. So it means √7 to what power equals √7. That's going to be to the first power. And in this next one, 6 to the log base 6 of 20. We take a look over here. We have log base A of A to the x equals x. That can be rewritten the other way as well. A to the log base A of x equals x. So a logarithm and an exponential function are opposites, right? So if we do log base A of A to the x, it's the same as A to the log base A of x, which is both equal x. It's just kind of opposite evaluation or opposite expressions. It's like if we do 5 plus 2 minus 2, we can just cancel the 2's out, we get 5. We can just cancel the log and the base A out with the A to just get the x. It's like saying A to what power equals A to the x power. Okay, it's gonna be x. So over here, 6 to the log base 6, that pretty much just cancels out and gives us 20. And that brings us to example 4. Use the one-to-one property of logarithms to simplify each expression. All right, so if we have a log base 3 on both sides of our equal sign, they can cancel out and leave us with just x equals 12. It's the simplest question we're doing all day. Okay, next one. We have just log on each side. Remember, that really means log base 10. But that can cancel out and leave us with 2x plus 1 equals 3x. And now I'm going to solve for x. So I'm going to subtract 2x to the other side. And we get x equals 1. And for letter C, I'm going to cross off the log base 4. So we get x squared minus 6 equals 10. So I can add 6 to the other side. And I get x equals plus or minus 4. Now, in this type of question, I really want to go back and check just to make sure that the answers I get don't make the inside of a logarithm negative. If I try 4 or negative 4, I'm going to get 16 minus 6. So this is still going to be 10 either way, so it worked out okay. Okay, let's take a look at some graphs. So on the same coordinate plane, we're going to sketch the graph of f of x equals 2 to the x and its inverse g of x equals log base 2 of x. This will graphically show us how these are inverses. Okay, so let's see. 2 to the x. So to graph that, which is from our previous lesson, I'm just going to take every x value, plug it in here, and see what I get. So 2 to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8, and so on. And let's see, over here, it's just going to kind of approach this horizontal asymptote. So I'm not going to spend too much time plotting those points, but I'm going to skip this. It'll look something like that. All right, and for the other expression, log base 2 of x, we can try that in our calculator if we want. I can show you how to type one of those in. And if you go to y equals, we clear this out, and we can go to math all the way down to the bottom as log base, and that lets you change the base. So we're going to do log base 2 of x. And when I graph this, this is what we're going to be working with here, but I'm going to go to the table so I can get some values to plot. So I have 1, 0, 2, 1, oops, 3, 1.5, 4, 2, 8, 3. And you can see that it's as if I took the x and the y value from each of these points and switched them, right? 8, 3 was on this curve, and 3, 8 was on the other curve. So this is going to be approaching a vertical asymptote here, and then it's going to go this way. And you can see that if I also plot y equals x, these are reflections over this line, which is the part of the definition of an inverse, right? So those are clearly inverse functions. And now for g of x, which I did in blue, let's find some of these properties. So the domain, we've got a vertical asymptote here, and then it only goes this way. So it's going to be from 0 to infinity. The range, though, is actually all real numbers. There's not a horizontal asymptote. So this keeps going down and this keeps going up, even though it curves as it goes up. The x-intercept. So here's our x-axis. We intercept it right here at 1, 0. And remember, these are interval notation, but this is an ordered pair, but the notation looks similar. We have on the blue curve, we have a vertical asymptote at x equals 0. And this is always increasing. All right, so there is what our graph of the logarithm looks like right here. Really, it's just answering the question, like, um, I mean, it's just switching the x and the y values from the other, so it's clearly the inverse. But let's keep going. Example 6. Evaluate each natural logarithm with a calculator, rounding to the nearest thousandth. Okay, so we're used to this by now, but now we have the natural logarithm, which means log base e. So there's two ways you could do this. We could go to math, go to log base, make the base e, and then type in 2 for this one. But there's a much quicker way on these calculators, at least, if you press ln for natural log and then type the 2, and you'll see you get the same answer. So it's 0.693. For the second one, natural log of -1. Oh, not real, because once again, it's saying e to what power equals -1, and that's never going to be -1. It's never going to be negative at all. But if we do natural log of 1 plus √2, we get 0.881. Okay. Example 7, last one here. Use the properties of natural logarithms to simplify each expression. Properties of natural logs are very similar to the properties of logs that we looked at earlier in example 4. But let's do some of these. So the natural log of 1 over e. I'm going to change 1 over e to e to the -1, right? Because if I flip the fraction, I make it a negative exponent. And natural log and e are opposites, so those can cancel out and just leave us with -1. In letter B, we have e to the natural log. Those are opposites, so those can cancel out and just leave us with 5. We have natural log of 1 over 3. The natural log of 1 means e to what power equals 1. And anything to the 0 power equals 1, even e. So this is really 0 over 3, which we can just simplify to 0. And in this last one, the natural log of e is 1. It means e to what power equals e. So this is really just 2 times 1, which is just 2. Okay, so there's your overview. The worksheet is fairly similar to the previous worksheet. And as always, the answer key is on Schoology for you to review. And let me know if you have any questions. Thank you very much.